Okay, we can probably start. I don't see the speaker.
I'm here.
Okay. Okay, so we start the session, and the speaker is Pei-Ming, and title is Ultraviolet Physics and Hawking Radiation. And I will discreetly tell you that it's 10 minutes, but everybody will hear it anyways. But when there are 10 minutes to the end, please.
Okay, thank you. Okay, so should I start now?
Yes, please.
Okay, thank you. So thank you. I'd like to thank the organizers for their kind invitation and apologize for not being able to be there. So today I'd like to talk about UV physics and Hawking radiation. Many researchers consider Hawking radiation insensitive to UV physics, although there is this Transplanckian problem. And let me first adjust my screen. However, in fact, we find that UV physics has the potential to significantly modify Hawking radiation. So in this talk, I'll explain why people didn't believe that UV physics would affect Hawking radiation and why we have some evidences against that belief. So although in this talk, I'll not talk about specific models of quantum geometry, but I think it would be interesting to see how different models of quantum spacetime could affect the result of Hawking radiation and have some impact on the information loss paradox. So a quick key question in this work is how robust Hawking radiation is. Is effective theory valid for the prediction of Hawking radiation? So according to Hawking, if we take the effective field theory valid at low energy, we predict Hawking radiation. On the other hand, it's been pointed out a long time ago by Tuft that actually, if you trace back a Hawking particle backward in time to a near horizon region, they become very high frequency Transplanckian modes. So in principle, the low energy effective theory is not reliable. However, people still believe that Hawking radiation is robust. We don't need UV physics. We only need low energy effective theory for the following reasons. The first reason is that this frequency for the outgoing mode is not Lorentz invariant. It is changing under a Lorentz boost. So you can make it arbitrarily large or small. Secondly, there is a so-called nice slice argument, so that you can choose time slices throughout the formation and evaporation of a black hole, such that for every time slice, there is no large curvature, and all the events could be at low energies. And so low energy effective theory should be valid. So is this true? This is one thing we will investigate. And also, there are toy models in which the dispersion relations are modified. And it's shown that through these models, in these models, somehow Hawking radiation persists, even though the calculation is modified. So what we'll talk about here is that actually there exists a Lorentz invariant UV energy scale. So UV physics is needed to describe these events. And we'll point out that if there is a UV cutoff in your theory, then actually Hawking radiation will be turned off. And So this could be the easiest, the simplest resolution to information loss paradox. And on the other hand, if there is no UV cutoff, then non-renormalizable interactions or higher derivative interactions representing the features of UV theory actually dominate over the calculation of Hawking radiation. So the free field effective theory calculation of Hawking radiation is actually not reliable. And also, finally, we'll point out some UV-IR effects that are ignored in the past in Hawking radiation calculation. So if you have questions, you can feel free to ask anytime. So let's start with reviewing Hawking radiation. So we are considering a physical black hole formed by the gravitational collapse of a spherical collapsing shell. So we have vertical axis for time and horizontal axis for space. In the past, we have a large spherical shell with very low density. So it's approximately in Minkowski background. And then as time goes on, eventually they fall into the event horizon. So for a given total mass m, you have a Schwarzschild radius a, which is equal to 2 times the mass and times the Planck length squared. So in this problem, we have a dimensionless quantity, which is the Schwarzschild radius a over Planck length. And we can use this as the order of magnitude estimate of physical quantities. And this is a very large number. So comparatively, numbers like 100 or 1000 is still of order 1 compared with a over Planck length to the first power, for example. And the origin of Hawking radiation is the fact that for freely falling observers and for distant observers, they have very different notions of time, or rather, they have very different time coordinate natural to them. So for an outgoing quantum mode, at large distances, you have approximate Minkowski space and you have approximate light cone coordinates little u and little v. On the other hand, for freely falling observers, they would have a different notion of light cone coordinates natural for them because they are freely falling together with the collapsing matter. So the collapsing matter is sort of at rest if the collapsing matter is falling at a finite, not light-like. So they would have this capital U, which is roughly the Kruskal coordinate, Kruskal light cone coordinate. And typically this coordinate capital U for freely falling observers is related to this little u for distant observers through exponential relation. So the key feature is that this exponential relation has an exponent which is little u over a, roughly u over the Schwarzschild radius. As a result of that, the scaling or the blue shift or red shift, depending on your perspective, is also exponential. So infinite time at large distances correspond to a very short time near the horizon. So for the freely falling observers, a very short period of time matched to a infinite time at large distances. So for little u going from minus infinity to infinity, capital U only goes from minus infinity to 0. So as a result of that, if you look at the wave packet, a normal wave packet at large distances, so here horizontal axis is little u, and at different little u, you can have a wave packet centered at a different u with a certain central frequency. But if you trace it backward in time to near horizon region, then in terms of this capital U, the blue wave packet would look like this down here, and orange wave packet look like this, and the green wave packet looked like a very, very narrow wave packet, like a very high frequency mode. So because of this exponential relation between the time coordinates for distant observers and time coordinates for freely falling observers, there's this large difference between the notion of wave packets for these observers. And as a result, when you have a positive frequency mode for little u, you have a combination of positive and negative frequency mode for capital U. So that's the origin of Hawking radiation. So Hawking pointed out that because of this exponential relation between capital U and little u, the frequency in terms of capital U, which I use capital omega to represent, is related to the frequency for little omega, which is the frequency for little u, through this exponential relation. So for Hawking radiation, in which little omega, the frequency at large distances is 1/a, the capital omega, or the frequency for freely falling observers, is exponentially larger. So even though a is a very large number, but because of this exponential factor, within a short period of time, you can have a very, very large frequency for fully falling observers. So this is the origin of the Transplanckian problem. Although here capital omega is still not Lorentz invariant, so the fact that this can be arbitrarily large is not implying the need of a UV theory yet. But it tells us that when you have a positive frequency mode in little u, it corresponds to a combination of positive and negative frequency modes in capital U. And this corresponds to a change of the notion of particle. And therefore, you have Hawking radiation from a Minkowski vacuum. So usually people say this implies information loss because this calculation for Hawking radiation only involves effective theory. We have a decoupling theorem saying that unless there are high energy events, low energy effective theory should give a very good approximation, and quantum gravity or string theory, they are not needed for the calculation. So if in the low energy effective theory, you cannot see any channel or not enough channels to transfer information from the collapsing matter to large distances, then you have information loss. And from the description we had earlier, the Hawking radiation is a result of the space-time geometry. So regardless of what kind of matter is collapsing, as long as they create the same gravitational background, you have this essentially the same Hawking radiation. So the information about, say, wave functions of the nucleus in the collapsing dust has no way of transferring its information to large distances through Hawking radiation, and therefore there is information loss. And there's a nice slice argument, which is considered to be rather rigorous to imply that there is no high energy event, or at least there is no need of any high energy event in this collapsing and evaporating process. And we'll talk about this and point out the loophole in that argument later. But because of this, people often believe that Hawking's calculation is robust and effective theory does predict information loss. So a key question is whether there are high energy events. So there are many, there's a huge literature. I'm listing some of the papers in which people argue that Hawking radiation is insensitive to UV physics, and or it's robust to some sense. So including some papers in which, for example, in the paper of Enru here on the universality of the Hawking effect, Enru and Schutzhold actually pointed out that there are ways of modifying the dispersion relation to change the result of Hawking radiation, but actually it takes some rather unnatural modification. So essentially, people have taken this as a statement that Hawking radiation is rather robust. And there are many other more recent papers on this topic. But here, our emphasis is on the point that whether low energy effective theory is enough. I mean, string theory or other theories of quantum gravity being a unitary theory, of course, will not lead to information loss. But the question is still, if you have decoupling theorem, if in principle there is no high energy event, then effective theory should be valid. And why do we get a result from effective theory which is not acceptable? So that's the main question we are asking right now. So let's talk about the nice slice argument. This is a picture again of a collapsing shell into a black hole, and the vertical red lines represent the horizon. And we have the dashed lines representing time slices. So in the infinite past, we have like rather smooth, flat time slices. But at later time, we would modify the time slices like that, such that it turns out that it's possible to choose the time slices such that when you look at a Hawking particle at large distances, the Hawking particle is at a very low energy with frequency 1/A. And also the space-time curvature, including the induced curvature on each time slice, can be small all this time. That is, the large curvature region near the singularity can be avoided for a very long period of time, throughout which a large portion of the black hole is already evaporated, and you already have a lot of information to be explained. So in this argument, it seems that it's possible to choose the time slices so that at no times observers on these time slices find high energy events, but they already have a puzzle about the information, where the information goes, whether the Hawking radiation contains information, etc. The entanglement entropy problem. So when you have these choices of time slices for these observers, according to the adiabatic theorem, if we have an initial state which is nearly Minkowski vacuum, and at any moment the curvature is of order 1/A or less, then the excitation arising through time evolution should not be much larger than order 1/A. And for a very large black hole, 1/A is a very small number. So our effective theory should remain valid. Theories like the standard model, well tested on the Earth, and should be valid, because for a large black hole, the curvature or the gravitational constant near the horizon could be much smaller than the gravity on the surface of the Earth. So there's no reason why the effect of gravity should change the picture completely. And so we would have a puzzle here. So usually we say because of the decoupling theorem, since there is no high energy event, effective theory should be valid. And then we have the puzzle. However, there is a loophole here. So the effective theory should be valid, but only for low energy phenomena. So if you have a laboratory in which you see no high energy events, everything has a small curvature and a low energy scale, then your effective theory should be valid for any prediction of low energy experiments. But if you carry out a high energy experiment, if you try to test, for example, whether there is a particle created within a Planckian scale region, when you do this, the uncertainty principle will actually allow you to violate energy conservation up to a scale determined by the uncertainty principle. So effective theory is valid for low energy events, but it breaks down if you are trying to use it to predict transplanckian experiments. So what is the transplanckian experiment here? Well, for a particle detected at large distances, you would have a energy 1/A for large distant observers, for distant observers. But you trace it backward in time, actually, it is at a very high energy with respect to these observers. So that's why actually the effective theory is insufficient to describe the evolution for these modes. So to be more specific, there is a Lorentz invariant UV cutoff here. I mean, there's a Lorentz invariant UV high energy scale here, not necessarily cutoff at this point. So if you consider the center of mass energy between the background of the collapsing matter and an outgoing quantum fluctuation, then the center of mass energy can be very large if you are considering a very high energy outgoing quantum mode. If the center of mass energy is much higher than the Planckian scale, then you need UV physics, and quantum gravity or other UV theory would be relevant. So for example, as an example of UV theory, we will consider other cases as well, but right now let's consider the simplest case in which the UV theory has a UV cutoff at the energy of Planckian mass m sub p. So then it says that the center of mass energy between this outgoing quantum and the collapsing matter should be smaller than Planck mass squared. So Pu is the outgoing momentum for the outgoing quantum mode, which turns into a Hawking particle at late times. And PV prime is the ingoing momentum for a particle in the collapsing matter, for example. But since the black hole has a Schwarzschild radius A, so clearly the momentum for any object in this collapsing matter must have an ingoing momentum larger than 1/A. So Pu times V prime should be actually larger than 1/A times the frequency for the outgoing mode, capital omega. So this gives you an upper bound on the value of capital omega as Planck mass squared times Schwarzschild radius A, which is much, much larger than the Planck mass. So indeed, in the usual sense, this could be so much larger than the Planck mass for a large black hole that you can ignore its existence. However, because of the exponential relation we pointed out earlier between the frequency capital omega for freely falling observers and the frequency little omega for distant observers, actually, this finite, although very large cutoff, could have an important implication. So although nice-slice argument does hold, there is indeed no high energy events in effective theory, because these outgoing modes are still quantum modes. They are not real particles they become real particles in Hawking radiation only at large distances. But what kind of particle they become, or how many of them there will be at large distances, has to do with the time evolution of these quantum modes in the near horizon region. And when these quantum modes evolve through the collapsing matter, they have a very large center of mass energy with the collapsing matter. And so their time evolution through the collapsing matter should be described in UV physics, and low energy effective theory is insufficient. So in this sense, when we look at a Hawking radiation particle, which is very low energy at large distances, they actually have a very large center of mass energy with the collapsing matter. And although it's not yet a high energy event because there is no particle yet, but the time evolution of the quantum mode depends on UV physics. So that's the point here. So this is a little bit like Wheeler's delayed choice experiment. So something happens here around the horizon, which needs the time evolution theory of UV physics, but you're not yet observing its effect until much, much later when they become Hawking particles at large distances. Of course, you could have designed certain experiments for, say, for fiducial observers in the near horizon region to observe them. But you can instead wait until the quantum modes, outgoing modes, go to large distances and see what is their quantum state after this time evolution. Okay, so the Transplanckian problem now is Lorentz invariant, has a Lorentz invariant meaning because of this large center of mass energy. So a particle of energy of order 1/A at large distances, it has a very large capital omega, which is exponentially large at later times, larger little u for distant observers. And specifically, in terms of the scrambling time, which is defined as the Schwarzschild radius A times log A, roughly that. So more precisely, we are counting the time at large distances in terms of scrambling time. So we ask what happens after integer n times the scrambling time. And you see that this magnitude of this frequency capital omega is actually A over Planck length to the power of n-1 times Planck mass. So it could be much, much larger than the upper bound we had on the previous page here, mp squared over A, as long as this little n is larger than 1, right? So in a few scrambling time, the frequency is so large that the center of mass energy between the collapsing matter and the outgoing quantum is much larger than the Planck mass. So that's the key point here. So is there any question? So
Any from the audience here?
Okay. So now let's talk about what actually happens. So we consider two cases. One case is you have a UV cutoff. The other case is no UV cutoff, but you have different types of UV theory. So when you have a UV cutoff, then we can ask what is the expectation value for the particle number corresponding to a certain particle with a certain wave function. So here we have the subscript omega 0 u0 representing a wave packet centered at the time u equal to u0 with a central frequency omega 0. And B and B dagger are the creation annihilation operators corresponding to such a particle, and n is the particle number. So you can compute the expectation value in n-root vacuum for this kind of particle. And in our paper, we find that it's possible to rewrite this expectation value in the following form, where you have this usual Planckian distribution factor in front, but it's multiplied by the relativistic density of the particle rho, integrated from -infinity to a certain number which depends on the cutoff energy scale, omega lambda. So omega lambda is the cutoff frequency for omega, which was Planck mass squared times structure radius. So you see that if this relativistic density of the wave packet is localized at a very late time, at a very large U0, such that U0 lies beyond this range of integration. So when U0 is much larger than the upper bound of integration, rho is very small and the integration is nearly zero, right? So if you are looking at a wave packet that arises at very late time, then this expectation value of such particles is very small. So what it predicts is that you could see Hawking radiation for a while, but after a few scrambling time, then the Hawking radiation should stop. And during this scrambling time, order of magnitude of Hawking radiation, the mass of the black hole is only a negligible fraction of its total mass for a large black hole. So usually, according to usual results, the evaporation time for a black hole is structure radius a to the cube. But now the time is only of order a times log a, so much, much smaller. So during this time, you can essentially ignore the mass lost through Hawking radiation. So what we see here is actually that when you have a UV cutoff at a Planck scale, then actually Hawking radiation is turned off after scrambling time. Now, in most models of quantum gravity, actually there is almost always some notion of minimum length, and correspondingly a notion of maximum energy or momentum. So we can take this as a hint that this is a likable possibility, and this could be also the simplest way to resolve the information loss paradox. Although actually when we talk about minimum length in quantum gravity, sometimes we don't really mean that there is a length scale that is really the smallest possible to talk about. So it would still be of interest to see how concrete models of quantum space-time could lead to different conclusions about Hawking radiation. But this is just one of the possibilities when you have a UV cutoff. So what we see is that UV cutoff implies Hawking radiation turns off after scrambling time. And if there is no UV cutoff, what happens? So what I'm going to talk about next is how large number of particles are predicted in Hawking radiation due to higher derivative non-renormalizable interactions between collapsing matter and outgoing radiation field. So if there's UV cutoff, then Hawking radiation disappears.
Yeah, 10 minutes.
Thank you. Okay, so but if there's no UV cutoff, then in your UV theory, you always have a low energy effective theory in which you have higher derivative non-renormalizable terms in your effective theory. And normally these non-renormalizable terms can be ignored because their couplings are weighed by negative powers of the Planck mass. So usually they are very small, they are ignorable in your calculation. But in our calculation for Hawking radiation, turns out that the contribution of these higher derivative interactions actually dominate over the usual free field approximation. So that's one thing. And also we find that there is a UV-IR effect in which Hawking radiation becomes sensitive to infrared cutoff. So in the following, I'll talk about these two aspects, and then I'll conclude. So firstly, when we consider effective theory for the interaction between collapsing matter and outgoing quantum radiation field, in the past, people have done calculations with renormalizable interactions, but ignored higher derivative interactions because they are not renormalizable. But if you do consider them, as an example, we consider this interaction term, which is Lorentz invariant locally. But when you consider the two fields phi1 and phi2, with phi1 representing the outgoing radiation field and phi2 representing the ingoing collapsing matter, then because either one has a larger momentum in the ingoing or outgoing direction, so this invariant term is dominated by this term in the second line, a U derivative to certain order on phi1 and V derivative on phi2. And this GUV, this metric component, is the factor in the Schwarzschild metric, which goes to infinity around the horizon. So you see that, again, there is a very large number when you have higher derivatives, because the higher the derivatives, the higher power of this large factor of GUV. If you have renormalizable term, actually, you can have at the most two derivatives, so one factor of GUV, and then that factor would actually cancel with the measure in the integration over space-time. So you get a finite number. But when you go to non-renormalizable higher derivative terms, you have a remaining negative power of 1 minus A over R. So in the end, if you just take this interaction and compute using the usual standard S matrix calculation technique, you see your result to be proportional to a positive power of the large frequency capital omega. So more precisely, you get an amplitude like this for particles with frequency 1 over A at large distances. And so it corresponds to a first order perturbation theory calculation with this diagram. Phi2 is collapsing matter, phi1 is outgoing quantum modes with the same energy as Hawking radiation. So this is the contribution of this non-renormalizable interaction to Hawking radiation, but it's exponentially large. So at larger U, you have exponentially large amplitude, and so very soon it dominates over usual results of Hawking radiation. So at the scrambling time, this exponential factor overweighs the very small, tiny factor in front. This tiny factor is there because it's a non-renormalizable interaction, but the exponential factor overweighs that number within a few scrambling time. So then you see that your effective theory is not reliable because higher derivative terms, you have less knowledge about these high derivative terms, but they have more important contributions to Hawking radiation. Also, there is this UV-IR connection similar to noncommutative field theory. So the point here is that here I'm considering the wavy red line representing a Big Bang. So you have collapsing matter originated from some initial state, which could be a Big Bang. And then you have outgoing mode represented by this red line, red curve. So at large distances, you may capture a particle and you chase it backward in time until it reaches the collapsing matter. But if there is a higher derivative interaction, then its modification to the wave equation could be such that the velocity of this outgoing quantum mode is nearly zero. So it's essentially following the collapsing matter for a very long time. So in our calculation, we considered a simple higher derivative interaction. And then you can see that at 10 times the scrambling time, so if you are detecting a particle at 10 times the scrambling time, then the duration of time for this quantum mode inside the collapsing matter could be as large as 10 to the 1000 times the age of universe. For k equal to 2 refers to this number k here, which depends on the power of the higher derivative, and k equal to 2 is the lowest higher derivative power. So let me conclude. So we have shown that actually Hawking radiation is sensitive to UV physics. The reason why we didn't notice that was we didn't keep track of the contribution of these non-renormalizable terms. And because we didn't consider the center of mass energy between the collapsing matter and the outgoing mode. So usually people just say we can always assume that the collapsing matter is weakly interacting with the outgoing mode, so we can ignore the interaction with the collapsing matter. But this is actually not the case when you consider their high frequency outgoing modes. And when there is a UV cutoff, Hawking radiation is killed after scrambling time. If there's no UV cutoff, non-renormalizable interactions are important. So either way, effective theory breaks down. Effective theory cannot give you a good prediction of Hawking radiation. And one comment I didn't have time to explain here, but there is no firewall here because I briefly mentioned that the quantum modes, even though they have very large center of mass energy with collapsing matter, but the outgoing modes were still quantum modes. So the quantum state of these high energy modes, their time evolution are affected by UV physics, but at that moment there was no particle, so you don't really see any high energy particle popping up in the near horizon region. So in the near horizon region, as long as you are still carrying out only low energy experiments, the low energy effective theory is still valid, and there is no high energy event. The high energy event is only tested at a much later time, like the Wheeler's delayed choice experiment. And so finally, in this talk, we only talk about, in principle, how UV physics can modify Hawking radiation. It would be interesting to see how concrete models of quantum spaces or quantum gravity could change Hawking radiation. Thank you.
Thank you. Yes, Robert Brandenberger.
Thank you for a very nice and clear talk. My question is, have you thought about connections with cosmology? So the Transplanckian, for example, connections with the Transplanckian censorship conjecture or with the back reaction time. My hypothesis would be that if you apply your ideas to cosmology, you will find that within a back reaction time, the effects that you are discussing will be important.
Yes, thank you, Robert. So I haven't really considered cosmology seriously, but yeah, intuitively, I agree with what you said. So in the past, again, so people didn't really well, I guess accept you, but well, and some others, I guess. But many people ignored these non-renormalizable interactions, and also the fact that even quantum modes, their time evolution is determined by the UV theory. So even though they are not real particles, but actually, if you actually do the calculation, then you will see the effect of UV theory for these modes. But yeah, so it would be very interesting to apply the same idea to cosmology. Thank you.
So if no one else has a question, I have another unrelated question. There are people who don't like remnant pictures. They say that there are some problems with the idea that black holes lead to remnants. Now, if you have a UV cutoff, then I think you get the remnant picture. So what is your view of, for example, Giddings's objections to solving the information loss problem using remnants?
So usually people don't like remnants because they assume that the remnants are small. They are small size, like a particle. So that brings some puzzles. But here, we still have a very large black hole. So the evaporation only brings out a negligible portion of the original mass of the black hole. So the black hole looks just essentially classical. So the portion of the mass evaporated before it stopped is like log A over A squared. So it's a tiny portion for a large black hole. So it's quite different from the remnant picture.
Yes, there is another question there. And then I see him first because I was studying. Okay, I was turning this way, so I saw you first, but please, Harold.
Hi, Pei-Ming.
Hi.
So basically, you consider two scenarios. So, of course, if there is no UV physics beyond the Planck scale, then okay, this seems fairly clear. But so, as soon as you have anything beyond the Planck scale, you will always have these non-renormalizable things in the effective action, right? So basically, you're saying that unless there really is a strict cutoff, all these computations somehow don't make sense, and there is a serious problem. Did I understand this right?
Yes, Harry. So for effective theory, there is always a problem. So the effective theory is never good enough to make prediction. And the cutoff is a simple example to imply that effective theory cannot be good enough, right? So even if you say you impose a cutoff in your effective theory just by hand, then you still predict something different. Then you can avoid the contribution of the higher derivatives, but you are still in problem. So no matter how you choose to unnaturally define your effective theory, there's no way to claim that they give you a robust or reliable prediction.
Okay, thanks.
Thank you.
I have a last question from Corfu, and then somebody will tell me if there are questions from the web, please.
Yes, thank you. It's the same as the first question, but for the different sign of cosmological constant. If you have ideas CFT, then on general grounds, any reasonable CFT, its gravitational description will have infinitely many of these non-renormalizable interactions and so on, but we don't expect any trouble. And maybe second part to the same question, do you actually need for this to work loops of graviton to be okay, or you can ignore that and just be okay with some UV renormalizable theory not including gravity?
Right. So I was having in mind something like a standard model, for example, without gravity. So that's what the kind of model Hawking used to make predictions. So for that kind of models, we have non-renormalizable terms, and when they are large, when they have large contributions, you say that the effective theory is not valid for such predictions. So that's what I was talking about. So if you have a UV completion in some way, then you would have the higher derivative terms giving a joint contribution, and the large contribution of each individual term could cancel and give you a finite number. So actually it would be very interesting to have a concrete model in which you have a well-defined UV limit and check what happens actually when you combine all the UV contributions together. I'm not sure, did I answer your question?
Thank you.
Okay, if somebody, don't know if there are questions from people outside that I don't see, but if there are, please speak loud. Otherwise, we go to the last speaker of the morning, who is Emmanuele Battista, and the title is Friedman-Robertson at the end. What is it? On the propagation across the big bounds in the open quantum. You say Friedman-Lemaitre-Robertson-Walker cosmology.
And does it work? Okay. Yeah. Okay, thanks. Okay. Sorry? Okay, thanks. So first of all, let me thank the organizer for providing me with the opportunity to be here. This is my first time in this conference because I've started working in this field very recently in collaboration with Harold Steinacker. And as the title suggests, I will describe the propagation of a scalar field across the big bounds in an open quantum Friedman-Robertson-Walker cosmology, arising within the context of the IKKT matrix theory. Okay, here let me give you an outline of this talk. I will start with a brief description of the main features of our background geometry, and after that I will perform a classical analysis of our Friedman-Robertson-Walker geometry involving the behavior of null and time-lag geodesics. After that, I will consider a quantum analysis where we will evaluate the propagator of the scalar field, and at the end I will have my concluding remarks. So let me start with the description of our background geometry. As I said, our framework is the IKKT matrix theory, where recently solutions have been found, which can be interpreted as 3+1 quantum geometries, leading to an open Friedman-Robertson-Walker cosmological model with the big bounds. And within this framework, our background four-dimensional space-time M31 can be described semi-classically as the projection of the fuzzy four-dimensional hyperboloid, which is obtained from 5 matrices, capital XA, interpreted as quantizations of 5 embedding functions, lowercase xa. Now, a convenient parametrization of the four-dimensional hyperboloid can be given as follows. Here R is the radius of the hyperboloid, and eta and chi are 2 variables fulfilling the role of a time variable, eta, and a radial variable, chi. Theta and phi are the usual spherical angles. And if we project the hyperboloid along the x4 axis, we obtain a two-sheeted cover of the region x mu less than or equal to r squared. And in this way, we obtain the following parameterization of our space-time. Here you can also see a picture of the projection pi from the hyperboloid to our space-time. And in these settings, the lower shift corresponds to a pre-bounce epoch where eta is negative. The upper shift is a post-bounce phase where eta is positive, whereas the big bounce occurs at eta equals 0. And in order to obtain the effective metric on our space-time, let me recall you that the background solution capital T mu of the matrix model leads to the following kinetic term, which is valid for any field phi. If we use the semi-classical approximation where the commutators gets replaced by the Poisson brackets, here T mu is the semi-classical limit of the background solution, then the kinetic term assumes the standard form where capital G mu nu is our effective SO31 invariant Friedman-Robertson-Walker metric. You can see the metric here, where d sigma squared is the invariant length element on the space-like three-dimensional hyperboloid. A of eta is the cosmic scale factor expressed as a function of eta. Recall that eta fulfills the role of a time variable. Of course, you can also express the scale factor in terms of the variable t, the cosmic time, by exploiting this relation linking dt to d eta. Okay, now that we have seen very briefly our background geometry, we can perform a classical analysis of this geometry involving the behavior of null time-like geodesics having constant theta and phi. It means they are a kind of radial geodesics because, yeah, sorry. Yeah, here, yeah. Where this, sorry?
Where does this then come from?
I mean, you start with this solution from this kinetic term, and this is the metric of this background solution, the effective metric from the semi-classical limit, yeah. Yeah, you're right, because I skipped all the details, of course. But if you start with this metric, with this kinetic term, and you just plug in this approximation, you don't know the form of this semi-classical, you're right, you're completely right. Then at the end, you end up with this semi-classical limit of the kinetic term, which can be written in terms of this metric. Yeah, I don't have enough time, so I could not give you all the details, but sorry. At the end, I will show you the paper where you can find some details or maybe the references. Okay, so thanks for this. Can I go on? Okay. So, as I said, this is our effective metric. We will perform, first of all, a classical analysis of our geometry. As I said, our geodesics are a kind of radial geodesics because chi fulfills the role of, is a kind of radial variable. Let's start with null geodesics. This is the equation for these geodesics. Here you can see the solution, and you can also see the plot of the solution chi of eta. Moreover, also the plot obtained by means of the embedding functions. And as you can see, the geodesics are continuous at the big bounds, eta equals 0. And the same will be valid also if we use the cosmic time t. Here you can see the solution chi of t for early times. Again, the geodesics is continuous at the big bounds. Moreover, also time-like geodesics have the same feature. Indeed, here you can see the time-like geodesics for a non-comoving observer, pi is the conserved momentum associated to the chi-translational killing vector field. And again, the geodesics are continuous at the big bounds. And also, if we consider the cosmic time t, the solution chi of t is well behaved at the big bounds. So our classical analysis shows that both null and time-like geodesics show no pathological behavior at the big bounds, which means that both massless and massive test particles are able to travel across the big bounds. The same conclusions, as we will see, are valid also at quantum level. And this leads us to the third and last part of this seminar, where I will perform a quantum analysis of our geometry, where we will evaluate the propagator of a scalar field having mass m. This propagator has been obtained by means of a path integral approach, which is provided by the underlying IKKT matrix theory. So for this reason, let me introduce the matrix D'Alembert operator box, which governs the propagation of phi. In the semi-classical limit, again, skipping all the details, we obtain this relation for box phi. If you bear in mind this relation, you can also work out the action for the field phi in the semi-classical limit, which assumes this form. Here, omega is the SO for one invariant volume form on the four-dimensional hyperboloid. Now, in order to obtain the propagator, we have worked out the spectrum of the box operator. So we have solved this equation. Lambda is the eigenvalue. In particular, we have solved this equation by means of this separation ansatz, where we have supposed that the eigenfunctions phi can be written as the product of three functions: the functions f of eta, g of chi, and the spherical harmonics of degree L and order m. Now, just plug in these ansatz in this equation, and you obtain that the functions f of eta and g of chi satisfy the following ordinary differential equations, where beta is a real valued constant whose value will be constrained in a moment. Now, upon solving this equation, we end up with this final form for the eigenvalues, which we have indicated with upsilon. These are the eigenvalues of the D'Alembert operator, and as you can see, they are continuous at eta equals 0, which means at the big bounds. They are square integrable oscillating functions of the space-time, and they are written in terms of the following functions: the Legendre function of first kind, of second kind, and as well, and of course, also the spherical harmonics. Here you can also see the degree and the order of these functions. As you can see, beta has been constrained to be less than -1. And note also that starting from the expression for S, which is the order of this Legendre function, we also can obtain the final form of the eigenvalue lambda. So now that we know the spectrum of the box operator, we are ready to obtain the propagator. Just recall here that Q has been introduced as the order of the Legendre function of the second kind, but it is interpreted as a typical momentum. Indeed, in order to obtain the propagator, we have considered the following regime. We have called it flat regime. I will explain why. And hereafter, it will be referred to as FR. In this regime, we require the following conditions. Chi is less than 1, and Q is much larger than L. It means that we are considering scales below the curvature scale, so distances below the curvature scale. And here, Q is a typical momentum. It means that we are ignoring the extreme infrared regime associated to the propagator. Now, why did we choose to call it flat? For two reasons. First of all, because by means of this condition, we will be able for late time to recover the usual Feynman propagator, as we will see. But flat is written in quotation marks because the same regime has been applied also to work out the propagator for early times, where the geometry is, strictly speaking, no longer flat. So this is just a name. And if you consider this regime, FR, we obtain the following two relations involving the Euler gamma function and the spherical Bessel functions, which means that in the flat regime, the eigenfunctions upsilon of the box operator assume this form. The first equation refers to the eigenfunctions for late times, eta going to plus infinity. The second refers to the eigenfunctions for early times. Eta is approaching 0, so it means near the big bounds. By means of these two relations, we have obtained the propagator of the scalar field. Let's start with the propagator for late times. It can be written as the sum of two contributions, a leading term and a sub-leading term. The leading term is indicated with the capital letter L, the sub-leading with the letters SL. The leading contribution can be written in this way, and up to the eta-dependent factor, which resembles the cosmic expansion, it resembles the standard Feynman propagator on a flat Minkowski space, as I said before. Indeed, recall that the scalar plane waves in R3 can be expanded in terms of the spherical harmonics in this way. This is the so-called Rayleigh equation. Now, by employing the Rayleigh equation, the propagator assumes this form. If you just compare this relation with our formula for the leading contribution, you will see that these two equations are analogous. So as I said, our propagator, the leading contribution to our late time propagator, recovers the Feynman propagator. Whereas the sub-leading contribution assumes this form, and via the exponential factor, which depends on the sum between eta and eta prime, it gives a sub-leading contribution as compared to the leading term, which depends on the other end on the difference between eta and eta prime. So for this reason, this is a leading term and this is a sub-leading term. Now let's consider the local propagator near the big bounds. So it means that eta and eta prime are approaching 0. This is the final form assumed by the local propagator, thanks. And from an analysis of this expression, it turns out that the early time propagator is bounded and well-defined. Moreover, by means of the exponential factor here, which depends on the difference between eta and eta prime, it gives rise to a standard correlation between 2 points lying on the same sheet of the space-time, which means that the 2 points x and x prime can lie either before or after the big bounds. Moreover, it also gives rise to a propagation between 2 points which are located on opposite sheets of the space-time and near the big bounds, which means that, likewise the classical case, a scalar field is allowed to travel across the big bounds. So, in conclusion, in this seminar, I've described a work which belongs to a research project aimed at investigating emergent space-time and gravity within the IKKT matrix theory, which is, as you know, closely related to the string theory. Indeed, within this framework, I've performed, first of all, a classical analysis of an open Friedman-Robertson-Walker cosmological model. In particular, I've employed general relativity tools to investigate the behavior of Nile and time-like geodesics. This analysis has proved that both massless and massive test particles are able to travel across the big bounds. The same conclusions are valid also at quantum level, where by means of quantum field theory techniques, we have evaluated the scalar field propagator, which on the one hand is able to recover the Feynman propagator for late times, and on the other, it allows a scalar field to travel across the big bounds for early times. Let me mention future perspective and open problems. First of all, let me stress that our analysis is restricted to non-interacting test particles. Indeed, for physical particles, we should take into account the infinitely strong interactions with the infinite matter density near the big bounds. And of course, this point should be deserves a careful analysis. Moreover, it is also important to investigate further the correlation between the pre-big bounds and the post-big bounds eras. This correlation is predicted by the form assumed by our propagator. And a last point which should be addressed is the propagation of fermions in our geometry, in our settings. So, for further details, you are all kindly invited to read this paper, which I've written in collaboration with Harold, where you will find more details. So, thanks.
Thank you. Are there
So I don't understand the philosophy in a sense, or I mean, why do you need to go through this IKKT model and all that? Why don't you just take the action and then you do your analysis? So what is the deep reason behind doing IKKT model, then solving some equations of motion, then taking some semi-classical limit to go to something that is quantum classical or classical gravity, or
yes.
semi-classical gravity?
Don't know what's going on. Okay, yeah. I mean, this is a model which arises within the IKKT matrix theory. I mean, this metric here does not solve, for example, Einstein field equations. So it is a solution expected within the semi-classical limit of the IKKT model, matrix theory. There you can find these solutions which give rise to this Friedman-Robertson-Walker cosmological model, open cosmological model. But let me stress once again, this is not a solution of Einstein field equation. So you cannot start with, let me say, the metric and...
No, but you can do semi-classical, I mean, quantum field theory and curved spacetime for any metric. It doesn't need to be a solution of the Einstein field equations. You can take this metric. That is not a hindrance in a sense. But okay, maybe we discuss
okay
later at coffee.
Okay.
Hi, I have a question. What is the two-point function between pre-Bowles era and post-Bowles era can teach you? The last the last slide.
Let me. Oh, this one.
No, next one. Yes. The correlation function. What can it teach you?
I mean, the correlation between these 2 points, because you're right, because this propagator allows you a propagation between 2 points which are near the big bounds, but one is after the big bounds and the other one lies before. So in this sense, there is this correlation, in the sense that the propagation across the big bounds is something which can happen according to this formula for our propagator.
Can you learn about singularity?
Sorry?
Can you learn about singularity at that at eta equals 0?
The singularity of what? Sorry.
Of eta equals 0.
Yeah.
Okay.
And which kind of singularity?
No, I mean, you study 2-point functions, so you can take some limit.
Yeah, there are. I mean, this is an important point. There are some singularities at the big bounds. As for this reason, I stress that this is only for non-interacting test particles. So those kind of singularities you are referring to should be addressed in a different way. This is, so you are right. Yeah, thanks. Thanks for pointing this out. And there was also here.
Behind.
Also from.
Please.
Yeah, thanks.
Maybe what I'm going to say is wrong, but wouldn't you have in the during times near the bounds strong effects due to the non-commutativity of the IKKT model that makes that even the notion of particle that travels through from one sector to another meaningless?
Yeah, it is related somehow to what he was asking, right? Yeah, yes, you are right. There are strong effects even at classical level near the big bounds. First of all, the curvature blows up. For example, I did not tell you, but the curvature blows up. For these reasons, I stress that here these are test particles which do not interact with the curvature, let me say, because there will be also this infinite matter density. So they will affect for sure my calculation, but How I cannot answer at the moment, but this is something which should be addressed. So thanks for pointing this out. Thanks.
Thank you. Okay. If there are no questions here,
I thought, okay.
and if there are no questions, no, there is a hand there. Yeah.
Yeah.
Yun-san, please ask.
Okay, thank you. So I would like to ask you about the construction of the background space-time. So you started from hyperboloid and make a projection to two sheets, and you identify these two sheets as pre-bounce and post-bounce era, right? Yes, yeah, that figure. But yeah, I don't quite understand how these two sheets are connected to each other through the big bounce, and how can these two era can be, well, connected continuously with some parameter like eta. So can you explain a bit about this?
Okay, maybe. Okay, first of all, okay, let me mention another point maybe that maybe can help, can explain this. When you consider this projection along the X4 axis, the pre-bounce phase is described also by negative values of X4, and the post-bounce phase is described by positive values of the X4 variable. And the big bounce is the region where x mu equals r squared. So you can connect, if you want, these three big and big bounce and post bounce. You have to consider this relation here and the value assumed by X4. That I answered the question. But at big bounce, x mu equals exactly r squared.
I see.
In general, it is less than or equal to r squared. Here it equals r squared. When X4 is positive, you have post bounce. When X4 is negative, you have pre-bounce. So hope that this, of course, there are many details that I cannot, I had no time to go through all the details.
Yeah, okay. Yeah, thank you. I think I got the idea. Yes, thank you.
Thanks. The no time is a good way to end the morning session. We are late, and people think the gancho, so the order has already arrived. And we reconvene again. Don't have the program with me, but I think at 4:30, no?
Yes. Okay.
Oh, sorry. Let's thank again the speaker again. The ceremony was not properly done. Sorry, Emmanuele. Okay, see you.